A gigantic concrete wall costing more than $12 billion is being built amid the raging waves along Japan's eastern coastline. Not to stop an ordinary storm, but to defend against one of the most terrifying natural disasters on Earth, tsunamis. From simulating the immense power of tsunami waves, drilling foundations more than 20 meters deep, pouring millions of cubic meters of concrete, to placing massive wave-dissipating blocks weighing several tons along the shore. This is one of the most expensive and controversial coastal construction campaigns in the modern world. How is Japan able to build such a colossal seawall along a constantly shifting coastline? And will this wall be strong enough to withstand even greater disasters in the future? Join Terran Works in today's video as we explore the answer. To understand why Japan is willing to spend billions of dollars constructing massive concrete seawalls along its coastline, we first need to look at the country's unique geological position. Japan sits directly on the boundary of several major tectonic plates, where the seafloor can suddenly rise or sink after powerful earthquakes. When this happens beneath the Pacific Ocean, millions of tons of water are displaced toward the coast at tremendous speeds, creating tsunamis whose destructive power far exceeds that of ordinary storms. We're a nation with countless cities, fishing villages, ports, and industrial zones located near the sea. Tsunamis are not just natural disasters. They are a direct threat to the survival of entire coastal communities. Before 2011, Japan was already considered one of the world's best prepared countries for tsunamis. Many coastal towns had seawalls, warning systems, evacuation routes, and strict earthquake-resistant building regulations. But the earthquake and tsunami on March 11, 2011, shattered that confidence. Seawalls that had been designed to withstand waves of around 8 meters were overtopped by walls of water reaching 12 to 15 meters in height. In many areas, the tsunami did not simply spill over the barriers. It swept away homes, vehicles, fishing boats, and entire coastal infrastructures deep inland. The disaster killed nearly 20,000 people, destroyed numerous towns, and triggered the Fukushima nuclear crisis. After that catastrophe, Japan realized the problem was not simply about building taller walls, but about completely rethinking its entire defense strategy. A tsunami seawall could no longer be designed as a simple barrier. It had to become an engineered system capable of absorbing impact forces, surviving overtopping waves, resisting foundation erosion, and most importantly, remaining standing even when pushed beyond its original design limits. In other words, Japan's goal was not to defeat tsunamis, but to slow them down, weaken their force, and buy precious extra minutes for people to evacuate. In a disaster, those few minutes can mean the difference between life and death. The construction of Japan's new tsunami seawall system did not begin with concrete. It began in laboratories. Engineers collected data from the 2011 tsunami and recreated the disaster inside massive hydraulic simulation tanks to study how the water struck the walls, overtopped them, and generated pressure on the foundations. Interestingly, real tsunamis do not look like the giant curling waves often seen in Hollywood movies. Instead, they resemble a rapidly rising flood, pushing an enormous volume of water deep inland. After countless experiments, Japan finalized a new design. Taller walls, wider foundations, thicker steel cores, and foundations driven more than 20 meters deep to resist sliding, settlement, and complete structural failure when the ocean strikes. Once the designs were completed, entire coastlines transformed into gigantic construction zones. Crews had to demolish old structures, relocate power lines and pipelines, and build temporary service roads so trucks, cranes, and excavators could access the sites. But the biggest challenge lay beneath the surface. Many coastal areas in Tohoku consist of soft sand and reclaimed soil, incapable of supporting millions of tons of concrete over decades. To solve this, engineers brought in enormous piling machines to drill deep underground and install steel and concrete piles, forming a load-bearing framework beneath the seawall. Vibratory rollers, compactors, and crushed stone spreaders then compressed the ground layer by layer, transforming unstable soil into a solid platform capable of supporting the immense weight of the entire structure. After stabilizing the ground, tracked excavators began digging enormous foundation pits, some reaching depths of more than 20 meters. But building next to the ocean is far more difficult than construction inland. To prevent seawater from flooding the worksite, construction teams installed cofferdams, temporary steel retaining walls, around the excavation areas. High-capacity pumps operated almost non-stop to remove seawater and keep the bottom dry enough for the first concrete pours. A strong tide, heavy rainfall, or abnormal wave conditions could delay the entire schedule. This became one of the most difficult phases of construction because the worksite sat directly at the constantly shifting boundary between land and sea. Once the foundations were completed, enormous steel reinforcement cages began taking shape. Each steel bar was cut, bent, welded, and connected into a massive skeleton buried deep inside the concrete structure. Heavy-duty crawler cranes lifted entire steel assemblies into position, while workers standing on scaffolding checked every joint and spacing for precision. Afterward, formwork panels were installed, and long-arm concrete pump trucks began pouring concrete section by section. Each wall segment, stretching dozens of meters in length, was poured, vibrated, cured, and inspected before crews moved on to the next section. The entire seawall system was not built as one continuous block of concrete, but as hundreds of highly precise interconnected segments forming a continuous defensive barrier along the coastline. On the ocean-facing side, Japan did not leave the seawalls exposed directly to tsunami impacts. Giant cranes continuously lifted massive wave-dissipating concrete blocks, such as tetrapods and other precast structures, weighing several tons each, placing them around the base of the walls. These specially shaped blocks are designed to break apart wave energy before the water can strike the main structure directly. When waves crash toward shore, the force is no longer concentrated against a flat concrete surface. Instead, the energy is scattered, redirected, and weakened through thousands of interlocked wave breakers stacked together. In some regions, engineers also use stepped or sloped wall surfaces to reduce the height and speed of overtopping water. At ports and harbors, where ships must continue operating daily, Japan could not simply build a completely sealed wall. Instead, engineers developed enormous steel tsunami floodgates powered by hydraulic systems. Some gates are suspended between massive concrete towers and can be lowered from above whenever tsunami warnings are issued. Others remain hidden beneath the seabed during normal operations, allowing ships to pass freely. But when danger approaches, hydraulic pistons raise the entire gate from underwater to seal off the harbor entrance. These structures require specially engineered corrosion-resistant steel, watertight hinges, and ultra-high-pressure locking systems capable of operating continuously in the harsh saltwater environment for decades. The greatest advantage of tsunami seawalls is not that they can completely stop every tsunami, but that they can slow the incoming water and reduce its destructive force before it reaches populated areas. In a disaster, just a few minutes can determine the survival of an entire community. If the wall can reduce the speed of the floodwaters or absorb part of the wave's energy, thousands of people gain precious extra time to reach higher ground before the ocean strikes. Those few minutes may allow warning systems to activate, students to evacuate from schools, elderly residents to be moved to safety, and entire towns to begin escaping before it is too late. Beyond saving lives, These seawall systems also help protect critical infrastructure, such as fishing ports, coastal highways, power stations, water treatment facilities, and industrial zones. If these facilities are destroyed, the consequences could continue for many years after the disaster itself. After 2011, many coastal communities were almost completely wiped off the map. As a result, the new seawalls became more than just concrete structures. They became symbols of Japan's effort to rebuild public confidence and restore a sense of safety. In many regions, these projects helped encourage residents to return home, reopen fishing ports, and rebuild coastal life. From an engineering perspective, the new system also represents a major advancement in disaster prevention technology. It consists not only of taller walls, but also deep foundations, reinforced steel cores, wave-dissipating blocks, harbor floodgates, drainage systems, and evacuation routes built behind the seawalls. Viewed from above, Japan's eastern coastline now resembles a continuous defensive line constructed from millions of cubic meters of concrete, tens of thousands of workers, and one of the largest coastal engineering campaigns in the modern world. But this is where the story becomes more complicated. A taller wall does not automatically guarantee absolute safety for the communities behind it. Tsunamis are extremely difficult to predict. Some occur only once every few decades, while others become mega-tsunamis far beyond any engineering scenario ever anticipated. If a wave exceeds the limits the wall was designed for, water can still overtop the barrier and cause severe flooding inland. Some researchers even worry that if a massive section of the wall were to collapse, the compressed water behind it could unleash an extremely powerful surge, similar to a dam failure. This highlights an important reality. No defense system is perfect. Tsunami seawalls are only one layer within a much larger protection network that includes early warning systems, evacuation routes, emergency drills, and smarter urban planning. If residents believe the wall alone can fully protect them and delay evacuation, those lost minutes could become the difference between life and death. For many coastal communities in Japan, the ocean has always been part of daily life. People grew up listening to the sound of waves and depended on fishing, tourism, and port activities for their livelihoods. But when massive concrete walls nearly 4 stories tall began rising along the coastline, they did more than block tsunamis. They also blocked the view of the sea itself. In some towns, residents described living behind the walls as feeling like living inside a fortress or a concrete prison. Beyond the social impact, the seawall system has also altered the coastal environment. Wave-dissipating blocks, sloped concrete surfaces, and continuous artificial barriers can affect beaches, ocean currents, and nearshore ecosystems. Because of this, many experts believe the future of tsunami protection cannot rely entirely on gray infrastructure like concrete alone. Instead, it should also incorporate green infrastructure, such as coastal forests, vegetated hills, and natural buffer zones to reduce tsunami impacts in a more sustainable way. More than a decade after the 2011 disaster, the gigantic concrete walls still stand there, stretching along Japan's eastern coastline like a scar of concrete left by history. They cannot erase what was lost, but they show how a nation chose to rise again after catastrophe. Massive piling machines, heavy-duty cranes, concrete pump trucks, hydraulic floodgates, and millions of wave-dissipating blocks have come together to create one of the most impressive coastal defense systems in the world.